Hello everyone, welcome to this video on some additional topics. So there are a few topics I want to mention in this lecture. One is about the function which is a common form, which is a squared plus bx plus c, right? So this is a quadratic function, right? It is also a more general form of a polynomial function of degree equals to 2. Right, so the degree of this function fx, degree of the function itself will be equal to 2. So the way we know that is that we just look at the biggest power function, which is this guy, and the power itself is 2. And a again is called the leading coefficient. So this term would be the leading term of the whole polynomial function, and it is actually represents the whole polynomial function when we do, for example, asymptotic analysis. But before that, let's look at a few properties. So one is, what if we want to find the minimum of f of x, right? So this is a common problem we would be dealing with. So the knowledge we know before we enter into the field of calculus is that what if we are asked to solve for this equation, right? So this is the equation we are used to, and we have the closed form solution, which is let me put out here, negative b. So I hope I'm correct in terms of laying out the closed form solution. So this is the case, right? When we set it equal to 0, right? However, this function itself, which is f of x, this is a more general function. It can go any positive, any negative, or any value, right? So this form is only specific to the quadratic function here we're looking at. And if we change some components in the function itself, this may not be usable, right? So we want to find general form that can give us the value of x, which we call the x star, that such as the value of the function is minimum, right? So how do we go about this? Now, one solution is that we can use the tool of taking the derivative, right? Differentiates the function itself so that we have the first derivative will be equal to 2ax plus b, right? And since this is a minimization problem, then actually you will be also asking the question whether the function is convex or concave, right? So this is a case that we find the minimum. This is a case we find the maximum. So to be able to say this function itself has a minimum, then we require should be positive. So it should be positive because it's going to be open in a shape like as a convex form. So this is one way to say that, because if it's concave, then it's going to be negative. A is going to be negative. So the other way to look at it is that we actually require the second derivative, which in this case will be equal to 2a, right? So the second derivative, depending on the sign of the second derivative. If it's positive, right, then it means convex, right? So this gives us a convex function. If, say, it is negative, then this gives us a concave function, right? So this is actually equivalent, but we're just looking at, so in the first case, we're jumping to the conclusion straight based on the properties of the quadratic function. In the second case, we are using the tool of the second derivative, which is another helpful tool to help us identify whether the function itself is convex or concave. Okay, back to here. So want to steer, so second derivative is to help us detect if the function is concave or convex. First derivative, however, is to help us locate where exactly is the minimum point. So how to do that? We just set it equal to 0 because we know at this specific point, right, this specific point, this loop is going to be 0. Then this gives us the solution, which is negative b over 2a, right? So this is using the differentiation, and it differentiates the function itself, so that we are working in the domain of the derivative, right? Not the original function. And the way we get the derivative is to actually do differentiation and come to the space of the derivative, right? Not the original function itself. So that's the power of calculus, right? We actually do a bit of transformation so that now, or instead of working with the original function, we now work with the derivative, right? We have something new, some new property about the original function with the derivative. Now that is our handle. Now we can work with the derivative, set it equals 0, right? Based on the property we have about the minimum point, right? Which is just by setting equal to 0, then we have this solution, which is our x star. So the second approach, which is does not really involve calculus, which also works fine, is that if we express x as express original expression as something like this, so I can say x plus m square plus n, right? Why do I write this? Because if I know m and n, and suppose I know, then I know this form itself is actually because I know a is bigger than 0, right? So it's actually has a minimum, because any function, right? Any square function is gonna be positive to 0, right? That's gonna be the same for this function, right? So if I time a here, right, also it becomes equal to 0. So if I plus n, so if I plus n here, that's gonna be bigger than or equal to n. So this is the range of this function, right? So always gonna be bigger than or equal to n. So the minimum point is n, right? So the minimum value is n. Now, how to get the minimum? We just set x equal to negative m, right? So that's our x star, assuming we know m and n. Now, so of course this it has its benefit, and the only thing we need to do is to re-express the original form here. So re-express it in a form like this. So this is called completing the squares, right? So we want to complete the squares, especially this term, such as these two equations are equal to each other. So re-express means that they are still the same expression, they just look different. And if they look something like this form, then it's very easy for us to get the solution. So that's what we want to do. And to be able to do that, then we can do a bit of reshuffling, because we just need to match the corresponding terms, the specifically the 0th degree term, first degree, and second degree. For these terms, both expressions should match in terms of their coefficients, right? Coefficients meaning the term that's multiplying all these different power terms. So let's do a bit of exercise by just taking the expression of this square term, and let me expand again. So ax squared plus, I'm combining the, okay, so I'm multiplying 2ma x plus am squared plus n. So this is what I have. Now, by matching the different terms of first term match, second term, which is the to the power of 1, right? So we have 2ma equals to b, right? So this is our second term. So by matching the corresponding terms, this gives us an equation to solve, right? Of course, we need the system equations because we have two unknowns, m and n. So the other one, am squared plus n should be equal to c. So now we actually do not need to solve for m and n. We just need to know what is the value of n, right? So which should be equal to b over 2a, right? So that's enough, because this is what we need to solve for x. So this is our solution. Plugging that in also gives us negative b over 2a. So that's exactly the same solution as we would get for using the first approach. So the second approach does not involve any calculus. it only happens when we actually using the property of the function itself. So which is that the domain of a square function itself is actually always positive, and we have the intuition is that we want to express in this form complete integrals, then we know the solution as a natural construct. Okay, so that's it for the first part, which is to look for the minimum of a function. It works the same as if we were looking for the maximum. So there's actually another approach, which is to say, okay, so let me just quickly talk about this third approach. Actually, it's related to the first approach, which is that third approach, which is say that we still find the okay, so we're still at this point where we have this this expression here, and by setting equal to 0, we have x equals to negative b over 2a. Now the question is, we're not sure whether this is a minimum point or the maximum point, right? So imagine this is a real line here, x, and this point gives us negative b over 2a. Now we're not sure whether the function is going to be positive or negative, right? So we need to do something about. I want to know some properties about the function form before and after these points, right? On the left side and the right side. So on the left side, if we say so on the left side is what if b is what if x, right? So we can just take one test example, right? Test number. So we just take one test number and then plug it in. So assume this is the so this is called so this is called a method that's actually used to construct the sign chart. This is a sign chart, right? So the sign is with respect to this function itself, so the derivative. So let me just cross this out because I'm talking about the derivative, right? So the derivative at this point is going to be 0, right? At this point, it's going to be 0. We want to say whether on the left side, on the right side, what happens. So if we just plug in a test number and say, so now this is my points, and I want to say if I plug in x equal to negative 2, right? What happens if say this is itself is negative, and if I plug in x equal to positive 2 on the right side, if it's positive, right? So what this gives us is that on the left side, our function is actually increasing. So if I look at the give some space, if I look at the function itself, which is f of x, now this is my middle point. So if it's decreasing, right? So because the derivative is negative, then it's decreasing. Then at this point, it's going to be 0, right? It's going to be flat derivative, flat slope, and then increasing. So that's again using the first derivative via the sign chart method to detect whether this function is concave or convex. So this does not use really the second derivative. We're just using the first derivative directly. So that also works. And of course, you have the inverse, which is that you have a chart, 0 and a positive, negative derivative. Then we have first decreasing, then increasing, then decreasing function. So that's actually also works. All right. Now let's come back to the points of the leading term in a polynomial function. So if I say my function itself is 3x squared plus 2x plus 1, and to be able to do some analysis about this function, we can say, what if when x goes to infinity, or specifically post-infinity, then what happens to f, right? So we know that this will go up faster than this term. So both will go up, but this will actually go up much faster. So in this case, right, we can say that when we have this condition that s goes to infinity, right? Now this will be approximated, right, or almost equal to just a leading term. Just a leading term, because we know that the growth curve of a linear line versus exponential line, right? So exponential, as x goes to the right, bigger and bigger, the distance is actually becoming larger and larger. So we know that the small scale, so for the terms that's not on the same scale, not on the same power or the same degree, then it's actually can be ignored. So we can only approximate it by this term. So that's, of course, that's an important condition, which is that we have x goes to infinity, right? So now, so how can this be used? So we can say we have this function 3x squared plus 2x plus 1, and we have, for example, 4x squared plus 5, right? So now this can be used when we are looking for the horizontal asymptotes, right? Horizontal asymptote. So now what this means is that what happens to the value of y or f of x, right? F of x. What is the value when x goes to infinity, right? So what happens to the value when x goes to infinity, and if that's a value, then that is the value which I call the horizontal asymptote. So how do you solve that? And of course, you can naturally add a condition. What happens to this expression, the value of the y or f of x, when x goes to infinity? And we can know that this can actually be approximated by the term here. So by approximation, we can actually say equal to, because now we are at the infinite case, right? So we are looking at the limiting condition. So they will be just equal to 3x squared over 4x, because now x is actually going to infinity, right? Let me add this condition as well. Okay, so we have the terms of the same degree, then we can just cancel them out. So the result is naturally 3 over 4, right? 3 over 4. So however, if say let me change the setting here to say that if I'm looking at power of 1 in the bottom, right, in the bottom part, then I would have 3x squared over 4x, right? Then cancel 1x, so 3x over 4. In this case, then my result will be that the limit itself is also increasing as x goes to infinity, right? That means that I do not have a constant asymptote, horizontal asymptote. That means that this horizontal asymptote does not exist, right? Does not exist. So that's the second case. However, if I change the order here to say that I want, for example, this is 3, then what happens is that I have 3x squared and 4x cubed. Then this gives me 3 and 4x. So as x goes to infinity, becomes very big, the whole denominator is very big, and then causing the whole term to be very small, and you eventually go to 0, right? Because it's going to be ever so small. So that means that 0 is my horizontal asymptote. All right. So there was another way to analyze this problem instead of doing the asymptote analysis. So the approach is that we can actually re-express the original expression as something like this. So we can still have these. Then we are looking at first we are looking so we're looking at the leading power function or the leading power function, which is x cubed. Right? So first we'll look at the leading term from both sides. Now this is x squared, this is x cubed. Then we know that, okay, x cubed is my biggest power, right? Then we just divide it. So divide x cubed from both sides, right? So from the bottom and from the top. So we have 3 over x plus 2 over x squared plus 1 over x cubed. And then here bottom we have 4 plus 5 x cubed. So now what we have here is that as x goes to infinity, now we have a few terms that's gonna be going to 0. So this is gonna be 0 because the bottom, the denominator is gonna be very big. So this also becomes 0. This becomes 0, 0, right? What we have is 4 over 0. 0, 4, we have 0 as well. So this is another way to analyze the problem by just you taking advantage of the fact that if x, right, goes to infinity, then the whole term will be 0. So this is a key insight, and it happens. It's actually same for x squared, x cubed, or any power. Okay, so basically, okay. So if x goes to okay, so if x approaches 0, right, let me change the perspective. So here I have a limit. If x is approaching 0, then this whole term is actually becoming bigger and bigger, right? So that's just a change of perspective. Okay, so that's it about this additional topic, and thanks for watching.